everybody. So we're going to continue our discussion of group homomorphisms by talking about the kernel of a homomorphism. And as we'll see, the kernel of a homomorphism are the things in the domain group which map to the identity in the codomain group. And kernels are somewhat like if you've taken linear algebra and you've looked at linear transformations, then the null space of a linear transformation is the set of things in the domain vector space which map to 0 in the codomain vector space. And if you try to understand a linear transformation, it's really important to understand its null space or its kernel. And that's going to be the case here in our discussion of group homomorphisms. So let me begin by just restating the definition that I used a minute ago, which is that if you have a homomorphism phi from one group G to another group H, its kernel is the preimage of the identity of H. So it's the set of G and G such that phi of G is EH. It's the set of things which map to the identity. So let's look at some examples of this. So let's go back to the homomorphisms that I used as examples earlier on and see what the kernels might be in those cases. So remember, the first one I looked at was the map which takes a permutation in Sn to 0 or 1 in Z mod 2, depending on whether it's even or odd. So the kernel of this phi is going to be the set of permutations in Sn such that phi of sigma is 0 in Z2. And that's exactly the set of sigmas such that sigma is even, because of the way the map was defined. Phi of sigma is 0 if you're even, and it's 1 if you're odd. And the kernel of this set of permutations is actually something that we introduced before. It's a subgroup of the symmetric group called the alternating group. So the alternating group on n elements is the kernel of phi, where phi is the sign phi is the sign homomorphism. And another example we looked at was the determinant map. Remember, that was just the map which sends G goes to the determinant of G. And the kernel of the determinant map is the set of matrices G such that the determinant is the identity element in R star. But the identity element R star is it's just 1. I mean, R star is the multiplicative group of real numbers, and the identity element is 1. So the kernel of the determinant map are the matrices of determinant 1. And again, that's a group that we've talked about before. It's called SL2R. So SL2R is the kernel of the determinant homomorphism. What about the map that I talked about where you have an arbitrary group and you take the map phi from Z to G given by phi of n equals G to the n? So the first thing to notice about this is that by our previous work, phi of Z is a subgroup of G. Remember, the image of any subgroup of Z, and in particular Z itself, is a subgroup of G, which is the codomain group, where G is any group, and the map is phi of n is G to the n. And what subgroup is it? Well, phi of Z consists of the set of G to the n for n in Z. And this is a group we've studied a lot. It's the cyclic subgroup generated by G. So the image of Z under the map phi is the cyclic subgroup generated by G. What's the kernel of phi? Well, the kernel of phi is the set of integers n in Z. Let's not use n because I used n up there. Let's use k, such that G to the k is the identity. Now, what do we know about the integers k such that G to the k is equal to the identity? Well, what we know is that G to the k is equal to the identity if and only if the order of G, which is the smallest k such that g to the k is equal to the identity, divides k. Or it could happen that g has infinite order. And if g has infinite order, that means that these powers are all different, and the only time that you get g to the k equals e is when k is 0. So the kernel of this map is either 0 if g has infinite order, or it's precisely the multiples of the order of g. So again, you'll notice that the kernel is a subgroup. It's either the trivial subgroup, or it's the subgroup consisting of the multiples of the order of the element if you have finite order. What about the map cis from R to T? Well, here the condition is, when is cis of R equal to 1? Because 1 is the identity in T. Remember, these are, so T here is complex numbers of absolute value 1 under multiplication, and the identity element is 1. So what does it mean for cis of R to equal 1? Well, cis of R is cosine R plus I sine R, and that's equal to 1 if and only if the cosine of R is 1 and the sine of R is 0. And when does that happen? Well, if you draw a little picture here, the only time the cosine of R is equal to 1 is if, and the sine of R is equal to 0 is only if you happen to be, have gone an integer number of times around the circle. So this is the same thing as saying that R, remember, R can be any real number, but if R is a multiple of 2 pi times an integer, then you're going to get cosine of R to be equal to 1 and sine of R to be equal to 0, and that's the only case. So the kernel is 2 pi z, which is a subgroup of R. It's the collection of integer multiples of the number 2 pi. And just to summarize, remember that we showed that in our big sort of list of properties, we showed that if H2, well, if you have phi from G to H is a homomorphism, and we had a subgroup K in H is normal, then we showed that phi inverse of K in G is normal. And the thing about the trivial subgroup is that it's always normal. And the reason is, I mean, it's kind of silly, but if you take H, EH, H inverse, you're just looking at the element H, EH, H inverse, but the identity element commutes with everything. So the H's cancel. And so in particular, it's the case that phi inverse of the identity element in H is always a normal subgroup. And in fact, we that's consistent with what we saw earlier. Remember the cases that we saw the alternating group, which was normal in Sn. We showed, I mean, we checked actually that the special linear group SL2R is normal in GL2R. We worked out what the cosets were. Remember, they were the multiples, they were just it was R star. We worked out the cosets here. There's only 2 cosets. And then in the other 2 examples, the groups were abelian. And of course, every subgroup of an abelian group is normal. So that's maybe not so striking that we would have gotten normal subgroups. But it's a structural fact of the homomorphism property of phi and the fact that the trivial subgroup is always normal, that the kernel of any homomorphism is a normal subgroup. And what's remarkably true is that, in fact, this is going to turn out to be an if and only if statement. That is to say, the normal subgroups are exactly the kernels of homomorphisms. And the way we're going to prove, we've already shown one direction. We've shown that if you have a homomorphism, then the kernel is a normal subgroup. The next thing we're going to do is if you have a normal subgroup, we're going to produce a homomorphism which has that subgroup as its kernel. And that's going to be the discussion in the next part of this chapter.